Hello students, welcome to Vista's Learning. This is Shruti, your chemistry tutor. We are in 11th standard. Students, we Vista's Learning provide you the quality education for all. Yes. So here, we are in P block elements. As we know, this is 11th chapter. And we have already started this chapter. Hence, we have the lecturing class 4 here. Got it? So what do we have already studied in our previous classes? Do you remember it? Yes, we have studied about the boron family. Now we are going ahead with the sixth, that is carbon family. Now we can see here the carbon family, introduction of 14th group elements, right? So what you can speak about this carbon family? You just have a remembrance on this. I'll be back. So do you remember, students, what does this carbon family says? Yes, it will be the 14 group elements where we have the elements starting from carbon, as we say the carbon family. Here we have silicon, germanium, tin, lead and fleruvium, where these are the elements present in 14 group elements. And carbon is the 17th most abundant element by mass in the Earth's crust. And it is widely distributed in nature in free as well as in combined state. Free, as we say, the allotropes of carbon, they are in the free state, whereas when combined form, for example, carbon monoxide, carbon dioxide and glucose are the examples, the combined form of this carbon. In elemental state, it is available as coal, graphite and as diamond. And in combined state, as I said, we can get many metal carbonates, hydrocarbons and carbon dioxide as a gas. It is having 0.03% and as an air. So here we can go ahead with silica, the second member. Silica is also present in the form of combined form as a silicates, where you have many ore forms of the silica. You can see the mica, quartz, and these are some of the examples. And that silica is used to form ceramics, cement, and glasses too. So here, when we come back with the germanium, yeah, here next is germanium after the tin, where we found this very traces of germanium is been found in the Earth's crust, and important semiconductor material. Means we use this germanium for the semiconductors. So who gave this? Mendeleev, who have the idea where in the empty space he have been given, there we have the germanium which is been found. Later we have the tin. Sn is the stannous. The stannous is the tin. It is a Greek name for tin, where we get the symbol from Sn. So next we have the ore of the tin, and this is the lead, which we call it as plumbum. So here also we have the Latin word for lead, which we call it as plumbum, and lead is used for many purposes and it is very luscious in nature. Galena is the one of the ore where we get the lead from. It is in lead sulfide. So PBS is the lead sulfide. Galena is the ore where we get the combined form of lead in this ore. So here, one, we can just say this, carbon is the most versatile element in the world. As we know, it is combining with many substances. So, its combination with other elements such as dihydrogen, that is hydrogen gas, dioxygen, chlorine, sulfur provides an astonishing array of materials ranging from living tissues to drugs and plastics. That means variety of substances or molecules or compounds can be formed which are in different uses by this carbon. It can combine with many substances, many other elements which come under tissues, living substances, even drugs and plastics. Organic chemistry is devoted to, what do you mean by organic chemistry? The study of carbon and its compounds, right? So, organic chemistry is devoted to carbon combined compounds, means it will be combining with many substances. So, we group the study of carbon and its compounds as organic chemistry. So, it is an essential constituent of all living organisms. As we know, for gaining energy, carbohydrates is very much important for the body. So, carbohydrates, what do you mean by carbohydrates? Which contain carbon, hydrogen and oxygen. That is called as carbohydrates. So, that is also a form of or combined form of carbon. So, that is very much important for living organisms. And this carbon has the isotopes. It has the isotope of carbon-12, carbon-13 and traces of carbon-14 are found. So, naturally occurring carbon contains two stable isotopes, that is carbon-13 and carbon-12, whereas the one which is radioactive is carbon-14. So, 12 carbon or carbon-12 and carbon-13 are the stable isotopes. Okay. And in addition to this, we have the one more, that is third one, which is carbon-14. We say, and it is radioactive, it decays soon. So here we have the study of this. So we have started with this, right? So after lead, we have the galena, which has been the form of this. And here, as I said, semiconductors, this silicon and germanium will be used in this transistors and chips as a semiconductors. They are useful here. So here, which are the elements which are used in transistors? We use silicon and germanium. So we can get the electronic configuration of carbon, silicon, germanium, tin and lead here. As we know, these all are 14 group elements. We have the 4 valence electrons in the outermost shell. As you can see here, 2s2, 2p2. So 3s2, 3p2. 4p, this should be 4p2. As we see here, it should be 4s2, 4p2. Okay, it is 4s2. This is 3d10. And here, as we see, 5s2, 5p2, and 6s2 and 6p2 are the electronic configuration which has been formed by 14 group elements. As we see in general in periodic table, we go down, the size will be increasing. As in the 14 group also, down the group what happens? The size increases. So you can see here from carbon, silicon, germanium, tin or stannous and plumbum or lead, down the group what happens? The size increases. So here, as we said about the electronic configuration, the chemical properties depend on this electronic configuration. So, if it is lesser than 3 electrons in the outermost shell, what happens? They come as a metals. They can easily lose the electrons, but here they have 4. So, they cannot easily lose the electrons nor gain the electrons. So, they share the electrons and mainly the carbon will form the covalent compound instead of ionic compound. So we have the S and P block elements, which is called as representative elements. And ionization energy, if you see here, for 13th group and the 14th group elements compared to that of 13th group element, the ionization energy for 14th group element will be higher. But down the group, it really decreases, and the same thing happens with the 14 group elements also. Down the group, ionization energy decreases. As we say in general, ionization energy decreases down a column, and the small increase from tin to or stannous to plumbum is due to the poor shielding of the electrons, inner core electrons. Got it? So you can see here from tin to lead. As we know, F block elements will be there, P or D orbitals will be there. What happens? The slightly increase in size happens from stannous to lead. Got it? It is 706, whereas it is 741. And now we are speaking about the radius. If you take the radius here, across the period, what happens? Radius decreases. So from 13 to electronegativity depends on the radius, right? So what happens if you speak about this? So we were here speaking about the atomic radius. So what happens? As increase in the radius, the ionization energy also decreases. But only the exception is that stannous and lead, because stannous will be having 706, whereas lead will be having 741. It slightly increases due to the presence of inner electrons, inner core electrons. So elements of this carbon family, will just know about still more further things about the carbon family. So it is a radioactive isotope. Which one? 14, carbon 14, and it has the half-life of 5770 years and used in the radiocarbon dating. Silicon is the second largest or most abundant element on the Earth's crust and is present in the nature form of silica and silicates. We just saw the same thing. Silica is in presence of silicates, as it is the ores. You have 5 ores of silicates, silicon. Silicon is very important component of ceramics, glasses and cements, and germanium exists only in traces. Just now we just spoke about that, right? So this tin occurs mainly as cassiterite. It is the ore of tin. And stannous, we have it in the form of, or tin is in the form of oxide. So tin oxide or stannous oxide, and lead is present in the form of lead sulfide, which we call it as galena. The symbol for flerovium is Fl, and this is a radioactive element, the largest or the last element of this group. So this is synthetic one. We are preparing this, and radioactive element, ultra pure form of germanium and silicon are used to make transistors and semiconductors. As we know, we have just saw the video, right? This germanium and silicons are used as semiconductors, and it has been used in formation of transistors. It has the atomic number 114, atomic mass 289 gram per mole. The Fl will be having this, and the electronic configuration of flerovium is this. Okay, even that will be having 7s2 7p2 as the outermost electrons. It has been prepared only in a small amount. Its half-life is very short and its chemistry has not been established. It means it is having a very short life and it will decay soon. So when it is been decaying soon, we cannot study about it. Hence, the properties or chemical properties of this flerovium is not yet learnt. Next, the electronic configuration, as I showed you, the valence shell will have 4 electrons. NS2, NP2 is the normal general electronic configuration. And the inner core of the electronic configuration of elements in these groups also differ as in the 13 group elements. And what about the radius? As we know, they are having covalent radius, as 4 is the electrons in the outermost shell or valence shell. So what happens? They just share the electrons rather than donating or gaining the electrons. There is a considerable increase in covalent radius from carbon to silicon, but from silicon to lead it has a small decrease, and further what happens from zinc to so as we see from zinc to silicon to zinc to lead, we have small decrease as we have the filled electron d and f electrons or orbitals. This is about the melting point. We'll just come back to that. This is what we were speaking, right? Ionization energy. Ionization energy. So hope you understand this point. Zinc and lead will have the increase in radius. The ionization enthalpy, as we said just now, the first ionization enthalpy of the 14 group elements is higher than that of the 13 group element, means because it is having 4 electrons and it cannot easily give out the electrons, whereas in 13 group elements it has only 3 electrons, it can easily remove the outermost electron easily. So here the first ionization energy is higher than that of the 13 group element. The influence of inner core elements is visible here. In general, the ionization enthalpy decreases down the group, as we know. The small decrease in ionization enthalpy from silicon to germanium and then to stannous, and slightly increase in ionization enthalpy from zinc to lead is the consequence of poor shielding effect of the intervening d and f orbitals. So here, as the size completely increases, what happens? It cannot hold the electrons, outermost electrons. But here what happens, zinc and germanium, it will be having a smaller radius, easily it can hold on with the outermost electron. So here for zinc to lead, what happens? Ionization energy slightly decreases. From tin to lead, what happens? Ionization energy decreases. So they are the soft metals with having low melting point. If you see here, the carbon till lead, the melting point will be larger than that of the 13 group elements. If you take the example of aluminium and silicon, then you will get to know silicon is 1693, whereas aluminium is 933 Kelvin. So by this, 13 group elements will be having lesser boiling point or melting point than that of silicon, and this carbon family will be generally having, they will be generally having +4 or +2 state, and they can, all of them can hold +4 state. Which is stable than +4 and +2? We'll just discuss it. Electronegativities. Due to the smaller size, the elements of this group are slightly more electronegative compared to that of the 13 group elements. This size across the period, what happens? The size decreases. So due to the size decrease in size, here 13 group elements will have less electronegativity than that of these group elements. So next, the electronegativity values of the elements from silicon to lead are almost same. If you speak about the electronegativities here, from silicon to lead, the electron negativities will be almost same. And what about the physical properties? All the members of group 14 are solids, and carbon and silicon are non-metals, where germanium is a metalloid and lead and tin are the soft metals with low melting points. So melting points and boiling points of 14 group elements are much higher than that of the corresponding group 13 group. Don't get confused here, students. What happens here is that they have the soft metals. The tin and lead are soft metals and they have low melting points, but that is the low melting point generally. But if you compare with the group 13 elements, then they will be having the higher boiling and melting points. Here we are comparing with the previous 13 group elements, whereas here in general we are speaking that the 14 group elements will have low melting point. We'll just speak about this. So chemical properties, as we know, oxidation states and trends of chemical reactivities. Here 14 group elements have 4 electrons in the outermost shell. So they have the oxidation state which exhibits +4 state or +2 state. Carbon also exhibits negative oxidation states, that is till -4. And the sum of the first 4 ionization enthalpies is very high, very high, where the compounds in +4 oxidation states are generally covalent in nature. They are not ionic in nature. The heavier members tend to have +2 oxidation state. The heavier members of 14 group elements will have +2 than that of +4. So here you have the sequence where lead will be having +2 state than that of zinc and then that of germanium, where carbon and silicon mostly have +4 or -4 state. That is what we are discussing here. Just a while. This is ionization energy we spoke, right? So electron negativity, as we say, silicon will be having 1.8, gallium, stannous, and here you can see they will be having 1.8 to 1.9. So this will be having almost similar electronegativities when compared to that of 13 group elements. In 13 group elements, you will be having 1.5, 1.6, 1.7, 1.8. It is increasing, right? Excuse me. Whereas here, what happens? It will be having the similar electronic configuration, like electron negativities. So as I said, the physical properties here, the first carbon and silicon are non-metals, germanium is metalloid and other two tin and lead are metals. They are the soft metals and they have low melting point. Generally, these are the melting point as we just discussed. Generally, they will be having the low melting point, but compared to that of 13 group elements, they have higher melting point. As taking an example with aluminum silicon, silicon is having higher melting point than that of aluminum. Hope you understand this, students. And when we speak about oxidation state, generally this group will have +4 and +2, and we have +4 state mainly for carbon and silicon. And down the group, what happens? They will have +2 state, which is stable. As you can see, the methane will have 4 hydrogen atom and it can exhibit -4 state. Carbon and silicon can exhibit with -4 as it is combining with the electropositive element. The combining of addition of all the charges on the element should be equal to 0 on addition. Okay, here we have carbon dioxide where +4 state for carbon and oxygen will have -2 each. So we will be having -2 +4 -2. And this is the ethine where carbon will have 3 bonds each, where it is a covalent bond. So we don't have any charge for them. Instead, we have 1 minus because here we have one hydrogen with 1 plus, one carbon with 1 minus. Similarly, on the other side also, on addition, we get it as 0. The molecules, neutral molecules always will have 0 as a number, or always we have the charge as 0 because they are neutral. They don't have positive nor negative. If they have positive, they will be called as cations, whereas if they are negative, they will be called as anions. The oxidation state of tin and lead, if you see, here we have 2s orbitals, right? So they do not participate in the bonding. Heavier elements, as we see here, increasing tendency to have +2 oxidation state, right? Why do they have +2 oxidation state instead of +4? Outermost orbit will have 4 electrons, S2 and P2. Here also S2 and P2. But these S2 are not participating in bonding. Either they are not removed or gained. So they are paired and they cannot be easily given out. Compared to that of p orbital, s orbital is closer to that of the nucleus. So what happens? Here s orbital will not participate in bonding. Only 2 electrons can be given out, that is present in the p orbital, as these are heavy metals and their size is larger. So what happens? P orbital contains 2 electrons. Easily 2 electrons can be removed, not the other 2 electrons. So what happens? We have +2 oxidation state for heavier elements. It is due to the inavailability of Ns2 electrons of valence shell participating in bonding. As I said, we have +2 state for heavier elements. Why? Because the Ns2 or S2 outermost S2 electrons are not available for participating in bonding. The relative stability of these two oxidation states vary down the group. Carbon, silicon mostly show +2 oxidation state. They show +2 oxidation state, where germanium forms stable compounds with +4 state and very few compounds in +2 state. That means germanium can have +2 as well as +2 states. Tin forms compounds in both oxidation states, that is +4 and +2. Lead compounds in +2 states are stable and +4 are strong oxidizing agent. Why do we say this strong oxidizing agent? Because they can easily be reacted, whereas +2 are stable. Here also we call this +2 state of tin as reducing agent because they react easily than compared to that of +4 state. Here +4 state will be stable. So the tetravalent state of number of electrons around the central atom in a molecule. For example, carbon in carbon tetrachloride is 8, whereas Being electron precise molecules, they are normally not expected to act as electron acceptor nor electron donor. Why we are speaking about these things now? Because 13 group element we spoke about electron rich, electron deficient and electron precise compounds, right? So here when we speak about boron, we have 3 electrons in the outermost orbit. So it will react with 3 other 3 electrons of other element and they form the bonding. Even though they are reacting, what happens? We have only 6 electrons in the outermost shell, where for attaining the octet structure we require 8. But here 2 electrons are deficient. So we call this as deficient electron, like electron deficient molecule. Whereas this problem is not facing by 14 group elements, as they have 4 electrons in the outermost shell. They can easily share 4 electrons with other elements. So now each atom will have octet group easily. So that is what in 14 group elements, they are electron precise molecules and they are not electron acceptor or electron donor species. Although carbon cannot exceed its valency more than 4. You can see that other elements can have +6, whereas here in carbon group, carbon cannot exceed +4 because they have only 4 electrons. They can gain 4 nor they can give 4 electrons. It is because we don't have d orbital in carbon. As we spoke, the carbon is in second group and they cannot have d orbital because d starts from 3d, third orbit. And their halides undergo hydrolysis and have tendency to form complexes by accepting the electron pairs from donor species. As we say, they undergo the halides of carbon undergo the hydrolysis. So what happens? On hydrolysis, the halogen can be removed and we can add with the electron donor species. For example, species like silicon hexafluoride will have the fluoride, and germanium hexachloride, hexaaqua stannous exist where the hybridization of the central atom will be sp3d2. Why sp3d2 students? We have 6 electrons which is attached, 6 molecules or ligands. So we want 2 plus 3 plus 1. So it will be 6. Totally 6 hybrid orbitals we require. And here for these elements, silicon, germanium and stannous, d orbital is available. Vacant d orbital is available, so they can have the extension to 6 ligands, whereas for carbon we cannot extend from 4 oxidation state. So as we were speaking about oxidation state, here you can see carbon and silicon can have minus or negative state here. So till here we learned, right? As we see, this 5s and 6s are not available. So oxidation state, you can see carbon silicon will have +4 and -4, whereas for germanium till lead will be having +2 and +4, where +2 is more stable. So tin has either +2 or +4 oxidation number in compounds. So you can have SnCl2 and PbCl2. You can have this SnCl2 which has been giving electrons and forming Sn +4 also. So Sn +2 can be reduced to +4. So we can say it is a good reducing agent. It has been oxidized. As we know, the increase in oxidation state takes place Just a while. So, increase in oxidation state leads to the oxidation, right? So, it gives you the oxidation, and that electron which has been removed can be taken by other elements for reduction. So, we call Sn as reducing agent, whereas lead can gain the electron and become +2, and so it can reduce others, whereas it can oxidize others, and we call it as oxidizing agent. As we speak about tetravalent compounds, 8 electrons around the central atom, where carbon always obey this octet rule by combining with other elements, because it will be having 4 electrons and other electrons will combine with 4, each electron sharing with carbon and forms the electron. So here we have the expanded octet structure. As we know from silicon to lead, the d orbitals are present, whereas for d orbital is absent for carbon atom. So we cannot have the extension, as we see the extension for these complexes with sp3d2. As I said, the hexafluorosilicate and hexachloro germanium, whereas we have hexaqua stannous. So these are having the extension with their oxidation number, because they all have d orbital which is present, whereas for carbon it is not possible because carbon don't have the d orbital in the outermost shell. So next we are speaking about reactivity towards oxygen. So all members, when heated in oxygen, they form oxides. All these 14 group elements forms oxides of oxygen when reacted with oxygen. So there are mainly two types of oxides, monoxide and dioxide. The formula, you can just take it as MO or MO2 respectively. Why we get this MO or MO2 respectively? Monoxide or the dioxide. As we know, carbon can have plus or minus 2, plus or plus 4 or plus 2 or plus 4, whereas oxygen will have minus 2. So if carbon is having plus 2, then oxygen is having minus 2, they form CO, that is carbon monoxide. If they are having plus 4 and oxygen is having minus 2, ones are twos are, right? So on crisscross, what happens? CO2. So likewise, they can form MO or MO2 as depending on the oxidation state, whether it is plus 4 or plus 2. So this 14 group elements will have plus 4 or plus 2 oxidation state, and that leads to the chemical property where we can see the oxides are formed with monoxide or dioxides. Silicon monoxide only exists at higher temperatures. As we say, this will be having plus 4, which is stable. Oxides in higher oxidation states of elements are generally more acidic than that of lower oxidation state. That means carbon monoxide and carbon dioxide, if I take, carbon dioxide is more acidic compared to that of carbon monoxide. As we know, carbon monoxide is a neutral oxide, whereas carbon dioxide is acidic oxide. So we can say that if they have lower oxidation state, plus 2 and plus 4, if you say, the lower oxidation state will give you the less acidic nature of that oxide than that of the more oxidation state. In oxides, carbon dioxide, silicon oxide and germanium oxides, they all are acidic, whereas stannous and plumbum are amphoteric in nature. Why? Because they have the lesser electronegativity. Excuse me. They are metallic in nature also, whereas these two are non-metals and this is a metalloid, whereas these two, stannous and lead or plumbum, that will be in a metallic nature, so they will be having amphoteric in nature. And you can ask me that they should be in basic nature, but they are not, because they have 4 electrons in the outermost shell, so that also matters. So we can just give them as a amphoteric in nature. Among monoxides of carbon monoxide is a neutral, as I said, and germanium oxide or monoxide is distinctly the acidic in nature, whereas zinc oxide, stannous oxide and lead oxides are amphoteric in nature. You can see here lead and stannous monoxide as well as dioxide, both are amphoteric in nature. So when it is been reacted with water, carbon reacts with oxygen and it gives you carbon dioxide. So this carbon dioxide is been prepared and you have a huge energy released because it is a combustible thing. Carbon reacts with oxygen, gives a heavy energy, high energy for formation of carbon dioxide. So reactivity towards water. Carbon, silicon and germanium will not react with water. They are not affected with water, but tin decomposes steam to form dioxide and dihydrogen. That means in presence of tin, the water decomposes to hydrogen and oxygen gas. So in presence of tin or stannous, we have water which is been given as hydrogen gas and we have the dioxide of tin formed. Lead is unaffected by water, probably because of the protective lead film which is been formed. Means it will be having the outer layer which is been formed by the oxide. So what happens? It will not allow the lead to react. So here we have carbon, silicon and germanium which do not react with water. You need to remember this, students. They will not react with water, whereas tin, in presence of tin reacts with water to form tin. As I said, these three will not react with water, where tin reacts with water to form oxide of tin and gives out hydrogen gas. Whereas the lead will have the outer layer which is having the protective oxide film and that will not allow the lead to react with water. Hence, we don't have any reaction formed with water. Reaction with halogens. So these elements, halogens we know, fluorine, chlorine, bromine and iodine. Obviously, these 14 group elements will react with halogen to form MX2 or MX4, like how we have for oxygen. Likewise, they react with and form MX2. That is, if they have +2 or +4 state, then X will always have -1 state, right? So on crisscross method, we get M1 X2 and here M1 X4. So like how we have for oxygen, we'll get this as MX2 when cancellation on cancellation, we get this, whereas we have for halogen MX2, MX4, where X is fluorine, chlorine, bromine and iodine. Except carbon, all other elements react directly with halogen under suitable conditions to form their halides. Most of the metallic, these halides of 14 groups are covalent in nature. The central metal atom in these halides generally have sp3 hybridization and the molecules are tetrahedral in shape. If they have sp3, then they will be having 4 orbitals, hybrid orbitals, so they can form the tetrahedral shape. So they will be having sp3 hybrid, 4 sp3 hybrid orbitals, where each hybrid orbital will be linked with the other 4 halogen. Exceptions for stannous and the lead, which is ionic in nature. As we said, they are amphoteric, so they slightly change with the properties. They are ionic in nature, whereas other elements will have the covalent form. So here we can see the 14 group elements reacts with halogen to form their halides. So carbon forms CX4, silicon form SiX4, where other elements form X4 and X2. And mostly the covalent compound, this is the, they will be having 4 hybrid orbitals with sp3 hybridization and tetrahedral as a geometry. So this is the carbon tetrachloride, which is having tetrahedral geometry. And this is the chemical property. We'll just see through that. So lead iodide. Lead tetraiodide does not exist because lead and iodine bond initially formed during the reaction do not release enough energy. Means that is not more stable. So to unpair this 6s2, that means s2 electrons in the outermost shell, it is not so easy, and excite one of them to higher orbital to form the 4 unpaired electrons around the lead carbon. So it is not easily formed. It is not giving more energy. If the more energy is not released during the formation of bond, that means the bond which has been formed is not stable. Whereas you can find that when carbon is reacting with oxygen, more energy is released and it catches fire. That means the carbon monoxide or carbon dioxide is more stable than that of the carbon. So here the lead and the iodide bond is not stable. So very less energy is been released. Heavier members of germanium to lead are able to make halides with the formula mx2, as we say, that will be having oxidation state which is +2. Stability of dihalides increases down the group, and considering the thermal and the chemical stability of germanium, germanium will have tetrahalide germanium, which is, or germanium tetrahalide is more stable than that of germanium dihalide, whereas lead dihalide is more stable than that of lead tetrahalide. It is exactly different. You have to remember this. So germanium tetrahalide is more stable, whereas lead dihalide is more stable. Except carbon tetrachloride, other tetrahalides are easily hydrolyzed by water because central atom can accommodate lone pair of electrons from oxygen to form the complex. So what happens when they can accommodate the electron from oxygen which is present in the water, they can get the molecule which has been formed, or they can easily displace the chlorine and take the OH minus ion from the water. So hydrolysis can be understood by taking the example of silicon tetrachloride. What happens? You will be having silicon tetrachloride. When it is been reacted with water, water contains OH minus ion and H plus ions, right? These electron which is present in oxygen can easily be attracted by silicon and chlorine can be removed out. So it undergo hydrolysis by initially accepting lone pair of electrons from the water molecule in d orbital of silicon, finally leading to the formation of tetrahydroxide of silicon. So here we can see this carbon tetrachloride. Similarly, we have silicon tetrachloride, which is reacting with water. This water molecule will be forming just a while. So this will react with OH, and OH will be shifting to the silicon and chlorine will be removed out. Can you see this? So when we take this silicon tetrachloride, chlorine has been displaced. Can you see? The chlorine is slowly displaced by OH, and that chlorine which is been given out will go and combine with the hydrogen present in the water. So this water hydrogen will go with the chlorine which is been shifted, and we have OH which is been occupying the space which is been occupied by chlorine. So OH displaces chlorine, and chlorine which is coming out will attack with this hydrogen and form HCl. So this is what the reaction takes place. So tetrachloride zinc silicon tetrachloride with water gives you the silicon hydroxide, and 3 more molecules of water if you add, that will all replace all the chlorine atoms and forms OH tetrachlorides. So here we can see all the chlorine atoms is been displaced by chlorine forming tetrahydroxyl silicon or silicon tetrahydroxide with removal of 4, totally 4 HCl will be formed by formation of this complex. Hope you understand this, students. Good. So here again we can just go through this. Even in your textbook you can find this. When the water is present, lone pair of electrons present in the oxygen will be accepted by the d orbital of silicon, and hence the chlorine will be removed out. So we get OH which has been attached to the silicon and 1 chlorine atom will be removed. Likewise, addition of more hydrogen atom or water molecules, 3 more water molecules will lead to the removal of 3 chlorine atoms in displacing with the oxygen like hydroxyl group. So we get a silicic acid where H will also be present with the oxygen. So we have SiOH4 which is been formed during the displacement or reaction of silicon tetrachloride with water. So next we have most trending and the trends and the anomalous behavior of carbon. As we know, carbon don't have d orbital and it is the smallest size, smaller in size in the group, or it is smallest atom in the given group. It will be obviously differ from its other elements. The properties will be different, and so we are learning about the anomalous properties or behavior of carbon. Carbon also differs from rest of the members. As we say, it is having the smaller size and its electronic configuration will be very high. Higher ionization energy, as well as there is no d orbitals available. In carbon, s and p orbitals are available for bonding, and therefore it can have only 4 pair of electrons as it cannot extend further. This could limit the maximum covalency of 4, as I said just now. The other elements can expand due to the presence of d orbital that cannot be done by carbon. Carbon also has unique ability to form p-pi multiple bonds. This is very much important. The catenation property of carbon makes the more compounds by which carbon can bond with other carbon atom. That is the very good important thing which we have the property for carbon, which leads to the formation of many compounds of carbon. You can see it can form the p-pi multiple bond with itself. Means the same carbon atoms, even though they are of small size, that makes the p-pi multiple bonds, which is very high electronegative in nature. Few examples of multiple bonds you can see here, where carbon-carbon double bond, carbon-carbon double triple bond, and carbon-oxygen double bond, carbon-sulfur double bond, carbon-nitrogen triple bond. So these are the multiple bonds we say. If you have carbon-carbon single bond, that will be called as single bond. If you have more than two, like two and more than two, then we call it as multiple bonds. Heavier elements do not form this p-pi bonds because their atomic orbitals are too large and diffuse to have effective overlapping. You can see here, this is how we have px and pz orbital of the carbon. They can overlap and form the pi orbital. So they can form the pi bond. So these py and p, this is the py, this is the pz and pz, which are combining laterally to form pi bond. So this is the structure where carbon can form with itself. So carbon have these allotropes. As we know, diamond, the graphite and fullerenes are the examples. Here we have some of the compounds which is been formed by carbon. Carbon can link with oxygen by two double bonds. Here with carbon-carbon single bond, carbon-nitrogen single bond, and here we have carbon-oxygen and oxygen-carbon. Likewise, the carbon can form many groups. When they are having this many groups, you can see each one is different. This is acidic carboxylic group, COOH is present. This is amine. This is this is ester, whereas this is alkane. So we have many types of carbon atoms which is been formed. So as we have already studied about this, down the group the size increases. We have this exception, this where the stability of carbon to the stannous. So here carbon atom have the tendency to link with one another through the covalent bond. Covalent bond is the sharing of bonding to form a chain, and they form the rings. And this property is called as catenation. And this is because carbon-carbon bonds are very strong. Down the group, as we go down the group, size increases, electronegativity also decreases. So tendency to show catenation also decreases. So other elements cannot show the catenation. This can be clearly seen from bond enthalpies. As we know, we can see the order of catenation will be more for carbon, and it decreases for silicon and very less for germanium, and it is almost similar to that of germanium with stannous. So by this we finishes the properties of carbon and its compounds, and we are next learning about the allotropes or isotopes of carbon. We'll just speak about allotropes of carbon in the next class. Hope you understand this, students. If you have any doubts, you can get back to us in our web application www.v-learning.in. Thanks for watching Vista's Learning.